Okay, we are now recording, and I have a couple of more announcements to make, but I wanted to put it on Screencast-O-Matic before, rather than just announce it to 3 or 4 people. So, number one, there's some office hours adjustments, and there's going to be many of them for about 2 weeks now. Okay. Philip, right?
Yes, sir.
Okay, still learning names and faces. All right. First, well, it's not first, but number one, we'll start here. Normally on Fridays, I have office hours on the Birmingham campus from 7:45 to 11:45. Not this Friday. I've got a treatment coming up this Friday, and I've got to be there for labs at 6:30. Treatment starts sometime after 7:30. They say it's going to be about a 7-hour treatment. So I won't be on campus at all Friday, so don't go looking for it.
Milliliters?
What's that?
What's that, for 300 milliliters?
No, that was last Friday. This will be 1,000 milligrams.
Milligrams.
Yeah, milligrams, yeah. So it'll be a full dose this time. And last time, everything went well. I did break out with a rash once, but they gave me more Benadryl and it went away. But they stopped it while the rash was there. So I was still about 7 hours. So I don't know what we're going to do with more than 3 times as big a dose. I think they'll just speed it up a little. They say usually the first one is when you have your reactions. After that, your body gets adjusted to it. Oh, your lab? Okay. Does anyone else need a copy of last week's lab? Okay.
Is there any way I can make up that test?
Yeah.
I need to make that.
Yeah, okay. I would say if we finish a little early today, you might be able to do it at the end. Second?
I'll take one of his.
Okay.
If he doesn't make it.
Okay. Anyone else need this lab? Okay, you got it. Okay. So it'll be, I won't be here Friday. Okay. Now, almost connected with that, but it's a little separate. I have an appointment with my hematologist on Tuesday, this coming Tuesday, and he only sees patients on Tuesday mornings, only, okay? So that's going to mess up my 8 o'clock class and probably my 9:30 class. I think I'll be able to get the 11 o'clock class in on time. So sometime in the next week or two, I've got to make up those 2 classes. So this coming Thursday, day after tomorrow, I will be holding my Math 112 class from 12:30 until 1:45. So normally I have office hours then. Thursday I'll be here in the classroom then. So that's when I'll make up that class. We haven't decided when I'll make up differential equations, but that will be probably the following Tuesday. No, possibly the following Tuesday. We'll talk about that on Thursday when I meet with that class again. Okay, that done. Except for that, my office hours. Oh well, there is one more thing, and this isn't. Okay, this is more than a week away, so don't sweat it yet. But we do have a faculty meeting at 2:30, not day after tomorrow, Thursday, but the following Thursday. Okay. But I've already requested, just so you don't worry about it, requested and got permission to leave the meeting early so we won't miss class, okay? So I knew you would be worried about that, but don't sweat it. Now, if I'm not here right at 3:15, don't leave, I'll be here. It's just, we'll be right over there in Ethel Hall Auditorium, and I'll have to wait till a good time to get away. And if I'm a couple minutes late, I will be here a week from Thursday, okay? I may be a little late, but hopefully not too late. All right. Any questions? Let's go over quickly then where we are and what we're doing. Someone's already asked about Chapter 1 test. We have had the first lab and the first test. I've gotten some more of the labs in today. That's good. And as soon as you can get the test made up, that's good too. Anytime during my office hours, and as I said, my office hours are kind of crazy right now. But normally, I have office hours on, let me give you Tuesday, Thursday first, from 12:15 until 3:15, okay? So if you can come any of those times, that would be great. Now, this coming Thursday, I will have a class from 12:30 until 1:45, but you can come in and I can give you your test and put you in another room. And probably next Tuesday, I'll meet with that class probably 12:30 to 1:45, the one that I missed on that. So except for those two, I'll be here 12:15 to 3:15. Now, also, as I said, after class today, the lab probably won't take the full 2 hours, so the odds are you'll have time, if you're ready for it, to take the test then. Okay. Now, in Chapter 2, we've had the first lab in Chapter 2, and precious few people were here for it, and a few of you have gotten your labs today, so please try to get those in. We will have a lab today. We will stop class at 5:45 and have lab from 5:45 to 7:45. However, I don't think it'll take you a full 2 hours. Last Thursday did not take a full 2 hours. Okay, so this one might be a little longer, but not too much longer. Okay, but then if you want to try to make up something right after the lab today, that'll be fine. Thursday, my guess is we're going to have the lab probably from 5:15 to 7:15, and then the test on Chapter 2 from 7:15 to 7:45, or whenever you finish it. So let's plan for that. I think we'll finish the chapter today. I think we'll be pretty easy to finish the chapter today, and that means we'll have the test on Thursday, 7:15 to 7:45, which means the lab will be moved up to 5:15 to 7:15 on Thursday. Now, after we finish the chapter today, we'll be moving on to Chapter 3, which is a fairly long chapter itself. More than likely, we'll have 3 labs for it as well. For some reason, my projector, okay, I guess it is coming on now. Yeah. So, we'll be doing that. Any questions? Okay? So the odds are we're going to finish the chapter today, have the second lab today, and then on Thursday, we'll continue in Chapter 3. We'll start Chapter 3 today, continue in Chapter 3 on Thursday, then have the third lab from Chapter 2, and then have the test from Chapter 2. And then we'll pick up and go from there. Just about every day we'll have, from now on, we'll have either 2.5 hours of class, 2 hours of lab, or we'll have 2 hours of class, 2 hours of lab, and 30 minutes of test. Just depends on what pans out. Any questions? Okay. Let's move on to, we ended with example 2.14. We finished that one, and we were getting ready to do 2.15 when we ran out of time last time. So let me see if I can find, this is probably as good a place as any. 2.15, bottom of page 47. A student and her rowboat have a combined mass of 100 kilograms. So here, well, let me get my pen activated. It's not cooperating yet. There we go. So here we have the water, and here we have the boat in the water, and here we have the student sitting in the boat. Okay? I don't know if she's fishing or what, but she's sitting in her boat. Now, it tells us here, the student and her rowboat have a combined mass of,
Sorry about what page, Cheryl?
it's on page 47 in the new book. It'll be somewhere near that. It's example 2.15. Okay? So, combined mass of 100.0 kilograms. Okay? Now, she stands in the motionless boat. What does that tell you? Motionless boat.
Not moving.
Not moving. What parameter does that tell you something about? If it's not moving, what parameter do you know something about? What are the parameters we talked about in this chapter?
Mass.
Mass.
Density.
Okay, that was last chapter a little bit. Yeah, that's fine. Velocity.
Velocity.
Her initial velocity is 0. Now, she's supposed to be standing. I have her sitting, but that's okay. So, VI is equal to 0. Motionless boat to begin with. Standing in the motionless boat in calm water, she tosses a 5-kilogram rock out the back of the boat. Okay, the way I've drawn it, she's facing the wrong direction, but she's going to take this rock and throw it this way. And this, yeah, behind her, okay? So this rock, the mass of the rock is 5.00 kilograms, okay? No, 5.0 kilograms. Don't want to give any more precision than what they gave us. Okay, 5.0 kilograms. She throws it out the back of the boat with a velocity. So now the velocity of the rock is 5.0 meters per second. 5.0 meters per second. Mass of the rock, 5.0 kilograms. Velocity of the rock in the opposite direction toward the back is 5.0 meters per second. All right. What will be the resulting speed of the boat? So what are we looking for? Yeah, the V final for the boat. Yeah. Okay? V final for the boat. The initial for the boat was 0. Okay. And the mass of the boat and the woman and everything is 100 kilograms. So our question is, what is the velocity of the boat final? This is what we're looking for. How would you solve this problem? What are we dealing with? Momentum. Momentum is one of these conserved quantities. Speed is not conserved. Acceleration is not conserved. Mass is usually conserved. Displacement is usually not conserved. Very few things are conserved. Mass and momentum are two of those conserved quantities. We call them invariants. They don't change. Okay? What was the initial momentum of this boat? 0, because it was motionless. Okay? She has the rock in hand. She hasn't moved it. The boat's not moving. Calm water, the initial velocity, the initial momentum is 0. Now, when she throws the rock backwards at 5 meters per second, and it's got 5 kilograms of mass, what momentum does the rock have? What momentum does the rock have? Hint, the formula is right there. Right here. That is momentum. P is momentum. Newton called it the quantity of motion, the product of the mass times velocity. So what would be the momentum of the rock? 5.0 kilograms, that's the mass, times 5.0 meters per second. What does that give you? 25. What unit? Kilogram meter per second. Okay? Now we already said momentum of the system initially is 0. We've just given the rock 25 meters per second, kilogram meter per second momentum behind us. That means the boat, the woman, and everything else is going to have how much momentum forward? The same, because the total momentum, it has to still be 0. Momentum, by the way, is a vector quantity, okay, because velocity is a vector quantity. So if the rock is going backward at 25 kilogram meter per second, that means the boat is going forward at 25 meters per second. So momentum of the boat with the woman is the mass of the boat with the woman, that's the combined mass, times the final velocity of the boat. See how it works? And we know this final momentum is going to be 25 kilogram meter per second. What's the mass combined?
What's the mass combined?
Yeah, 100 kilograms, 100.0 kilograms. And the V final of the boat, that's what we're looking for. So if this is equal to 25, then how do we solve for the velocity of the boat? Divide both sides by 100.0 kilograms. Units are your friends. Don't forget them. Keep up with them. Kilograms cancel out. And that would give you 0.25 meters per second. Good unit for final velocity. And that's exactly what they get in the book. Okay. Now, when I first read the problem, I was not sure what to do, okay? Because if the combined mass, that would include the rock, wouldn't it? Okay? But they don't say anything about that. So say the woman and the boat combined mass, we'll assume the rock is separate. So when she throws that way, then that gives us that. I wasn't sure whether we should drop this to 95 or keep it 100. The more I read the problem, the more I... Because she threw the rock out. So I didn't know if the rock was part of the combined mass or not. But in reading the problem more carefully, I think it just means the student and her rowboat have a combined mass, not counting the rock. So that's why we left it 100. Okay? To me, that wasn't super clear, but it's okay. Any questions on momentum? Conservation of momentum. Okay? Now, next topic, it's also under momentum, but this is now the topic of, is impulse. Now, in everyday life, an impulse is something you just do all of a sudden. I just decided to go to the movies on an impulse, okay? That's not what we're talking about in physics. Physics is much more precise. How we define an impulse in physics is a force acting on an object for some time interval, okay? Force acting on an object for some time interval, okay? Now, that's one definition of an impulse. Force times a time interval. A result of an impulse always produces a change of momentum, a change in momentum. If a force is acting on an object over some time interval, it's going to change the momentum of the object, always. Now, bunches of applications of this, and since two of you are automotive, I don't know where the other guys are, and the rest of you are not, and they're giving these in terms of automotive, let's go back memory lane for when I was a boy child, long time ago. I can remember the early cars that our family had, because early on we didn't have many cars. We had a pickup truck, and that was about it. My uncle bought a station wagon just so we could all move around as a family. But one of the first cars I remember my dad buying, besides the pickup trucks, believe it was a Plymouth. I don't remember what the make was. But anyway, a long time ago. They haven't made Plymouths in years. So this was way back before then. Its dashboard was a hard metal dashboard. Okay? And it jutted out toward you. Okay? You know what they used to call the passenger seat?
Passenger seat?
Yeah. They used to call it the death seat. Because if you're ever in an accident, at least the driver had the steering wheel and column to cram into, and it might give a little bit. But that passenger seat, nothing there, okay? So if you were to have been in a car accident, and by the way, an impulse is a force acting on some time interval, okay? And let's say that you hit a tree or a bridge or something else like that. Let's say you were driving 60 miles an hour. That's the velocity. Your mass is whatever it was. And all of a sudden you hit this object that basically doesn't give very much, and you hit that dashboard, that metal dashboard, like that. You change momentum from your mass times 60 miles per hour, that's your initial momentum, to zero in a very, very short period of time, as in, let's say, 1,000th of a second, okay? Well, that force acting for that very short time period is going to be enormous, okay? Now, what I'll do, I'm going to come back and give these applications later. I think we need a little more math first, okay? Here is the formula, okay? And I'm going to give a little background here. What was our earlier definition when we did Newton's second law of net force? Do you remember what that was? Newton's second law. Formula for net force. Oh boy, one of the most famous equations in physics. Okay?
Nathan's not here yet, so just tell us.
Okay? Look on page 42, very bottom of the page, equation 2.5. Right-hand column, very bottom of the page. Unless you got a different book, you'll have to look around some. Very bottom of the second column on page 42.
Inversely proportional.
Okay?
Page 43.
Okay.
1 Newton equals, no.
Okay.
Page 42.
Very bottom of 42. Last thing on there, equation 2.5.
Okay, the acceleration of an object is therefore inversely proportional to its mass.
Okay.
Am I reading the wrong thing?
Okay. Do you have the next paragraph start, if we express?
Yes, sir. Okay, if we express force,
Okay.
then
How about by solving for F?
A.
Okay.
No.
Right
F
after
equals
that.
MA.
F equal MA. There it is. Okay. That's your Newton, your net force, F equal MA. Can anyone tell me what A is? Oh, sorry. Say again?
I was going to say acceleration.
Absolutely, it's acceleration. Can someone tell me how we define acceleration?
Yes. No.
Okay. Going back a little further. Okay.
Acceleration is the change of velocity over time.
Excellent, excellent. Change of velocity, and change is, thank you, okay? Change is delta, difference in velocity over the difference in time, right? Would you buy that? Now, what was M? Parameter for M, what does that stand for?
Mass.
Mass times the change of velocity, that would give you what? Mass times velocity from the previous thing?
Momentum.
Momentum is mass times velocity. So another way you could express this is change of momentum per change of time. Because mass times velocity is momentum, so that's why that. So that's where you get this equation right here. Force equals change of momentum over change of time. Okay? Now, this is P final minus P initial. That's what the change means, difference in. Always final minus initial. Divided minus because it's a difference. Divided by time. So, if you were traveling in a car and you hit something, your final momentum being 0, or your initial momentum being everything you had, then you have a huge change of momentum. Okay? Now, what is your force? Okay? Think of it this way. Multiply both sides of the equation by t, and then you have force acting over a time interval. I like to call it delta t. That gives you your change of momentum. That is your impulse. Force times a time interval, delta t, gives you your change of momentum, delta p. Now, let's go back to that concept of your momentum, say your mass, whatever it is, times 60 miles per hour, which is a pretty high velocity, right? Changing to 0 in about 1,000th of a second, that's going to be a huge, huge force. Extraordinarily huge. Because this is a pretty good sized momentum change divided by a very small time interval that's inversely proportional to time, so that's going to be very, very large. Okay. Now, a couple of cars later, it may have been our next car, but a couple of cars later, we never bought new cars. They were always used cars. I can remember one time we bought a new pickup truck. Never a new car, new pickup truck. And happened to be that time my younger brother went out to the new truck and took a nail and scratched his initials in the steering column of the new truck. I thought my dad's brand new, spanking new, smelling new, clean truck.
So where is he bigger at?
He was, he couldn't sit for a while. Okay. And, anyway, but that's beside the point. So the next car we had, or one of the next cars, I remember was a vast improvement over that first one. And that one, the metal dashboard had a little bit of padding on it. Remember when they put padding on the dashboard?
Still hard.
Still hard, but at least you had a padding. What did that padding do for you? A little bit. And what does that mean? That increased the time interval in which you hit it, because now you have to press that cushion in and it springs back a little. So now maybe rather than 1,000th of a second, it may have even been 1/10 of a second. But guess what? That's 100-fold decrease in force. Now, I just made up the numbers there. It may not have been that much. But if it changed it from 1,000th of a second, like that, to 1/10 of a second, then that's 100 times less force. Okay, 100 the force. That was a big improvement in my mind. Okay, Emmanuel's here. Okay. Now, a few years later, many years later, we took a long time before we swapped cars. The next thing, big improvement they had was what? After they padded the dash, they put in seat belts. Now, originally those seat belts were generally just belts. Not a shoulder thing, but just a belt. Okay? Now, what that did for you, if you hit something, then you were thrown forward, but it pulled you back at least some. So it kept you, in other words, it increases time interval even longer, over which the time you had to stop. It started off immediate stop. Now with the seat belt, you're thrown forward and back, so it may even take a second or two maybe. So now you've decreased that force by another factor of 10 to 100 just by the seat belt. Okay? Now with the seat belt though, you could either damage some internal organs or still reach the dashboard but with less impact. But then they came out with the shoulder harness. in addition to. I can remember the early cars had them separate. You had the seat belt here, and then you also had to fasten the shoulder harness in. That then almost kept you from reaching the dashboard. And by the way, by this time they were making no more metal but plastic or other dashboards that would give way. But fortunately, if you had your seat belt and shoulder harness on, you weren't even reaching. So now the time interval was even greater. So the force of the impact, if you did impact it, was much, much, much less. Okay? Now after seat belts and shoulder harness, what was the next improvement?
Airbag.
The airbag. Now what does the airbag do? Again, it comes out and now you have to press in the air and may never even reach the thing. So now your time interval is much, much greater, so the force is much, much less. Does that make sense? Okay? And in fact, just about any time that you have what you're calling padding or cushioning, that's what you're doing, increasing the time interval over which you have a time to stop. Now, I remember the 1996 Olympics in Atlanta, okay? They were the Summer Olympics. I wasn't there this day. We did go over for one day, I think, of tennis. I think is all we saw there, but it was fun to be there. But we were watching it on television, and I remember hearing about this. They didn't show it on TV, but there's one of these little young Chinese gymnasts, female gymnasts, who had this incredible vault. And what they do then was run just as fast as she could. And she could fly down that alleyway, jump off a springboard, go up into the air, come down on a pommel horse and do twisting and spinning and stuff like this. And where was she supposed to land? Up there, and what did they have there? Piles of padding. In fact, if you watch any of those, the gymnastics, padding everywhere. Okay? Because it increased the time interval over which you stop the fall. Exactly. But this gal, she went running super, super fast, hit that, but she got off balance and hit the pommel horse badly, and she wound up going that way rather than this way. And she happened to hit the gym floor, not the pads. Quadriplegic. Because the force of that impact, because that time interval was just instantaneous, was huge, crushed the bones in her neck and everything. It was really pretty sad. Okay? But if she had hit the padding, that would have been a much longer time interval. Hopefully no broken bones. But you watch, the high jumpers, especially those pole vaulters going way up there, but they come down on just a mountain of pads. Actually, my nephew had decided to do the pole vault when he was in high school. We thought it was crazy, but no one else was doing it, so he managed to do pretty well, comparatively. And anyway, but you land on just really deep padding there, and that's increasing the time interval. So the force, it's the same change of momentum, going from a very high rate of speed to zero, big change of momentum, but if you can increase the time interval, you decrease your force, big time. Now, on the subject of pole vaulting, this is just a dumb story. It really has nothing to do with impulse. But we have a good friend who is an excellent carpenter, okay? And he's done a lot of work around our house, in a couple of places, several things, and we're good friends with him too. And he told the story. He's a good athlete. You can just tell. He runs, he doesn't do it much anymore, but he used to. But when he was in high school, he said he was pretty fast, but not the fastest, okay? He was pretty good at the distance running, but not the best. Pretty good at the sprints, but not the best, okay? He just couldn't find anything he was the best at, And his coach said, and he was strong, he had a lot of skills, but he just wasn't the best at anything. He said, have you considered the decathlon? Does anyone know what that is?
What now?
Decathlon. Okay, what's a decade? 10 years. A decathlon is 10 different events. And he was good enough, fast enough and stuff, not to place first, maybe even second in all the things, but he was good enough in many things. He said, do the decathlon. It's a tough, tough, tough thing to do. And his sophomore year in high school, he came in third in the state. And the two guys that beat him were seniors. He said, I'm going to own this for the next 2 years. Well, he thought so. That summer the next summer after his sophomore year, they had a sports camp somewhere, probably in the area here. He was from Homewood, Alabama, by the way. And his coach signed him up so he could go to the sports camp and practice some of these things, and he was getting better at lots of things. And there was another kid, a big old kid, strong guy, from McAdory High School, who was there too, and he was doing the decathlon. I think he was a freshman, upcoming freshman, so he was younger than John. But he was doing great on just about everything.
Was it Bo Jackson?
You're absolutely right. It was Bo Jackson. He couldn't pole vault though. So John gave him a few tips and showed him and things. And he was such a good athlete, in just a few tries, after John helped him out some and stuff, he learned the pole vault. Wasn't very good at it, but he could do it. But he was so much better at all those other events, John never came in better than second, because Bo Jackson beat him the rest of his time in school. And you hit it right on the nose, Bo Jackson. James is here, right?
Thank you.
All right, good job. So anyway, that was just a dumb story since we were talking about pole vaulting, or I was talking about pole vaulting. So you see, impulse makes a big difference. So anytime you have padding, like, well, what's the big thing in football these days? Concussions, exactly. They're doing all they can, and they have improved helmets big time, even since I was in high school. Okay? They're bigger because they got so much more. They have that webbing inside that gives. They have the padding inside. But can you remember the pictures back way before my time? Those old guys? Leather helmets. The time interval for those things? A few tenths of a second maybe. Today, much less. We're talking about impulse. Impulse is a force acting over a time interval. That's what an impulse is. And if you can increase the time interval, you decrease the force. So that's where padding, yeah. That's all right.
I'm trying to say, well, you had mentioned like football helmets, like, I used to play football in high school, and like, we had some old helmets, all they had was like, I guess you can say styrofoam with padding.
Yeah.
And then once, I think in 2012, they started having these revolution helmets, where it's like air pockets inside the helmet.
Yes.
And each year that came out, they started increasing the air pockets to where they were making more cushion.
Right.
The only problem with that is you just gotta keep pumping up again.
Right, exactly.
Holding, you gotta turn up.
Yeah, and if the air is not there, then you have the same problem you had before. But everything you did there was trying to increase the time interval to decrease the force. Because frankly, boy, these guys that repeated licks on the head, they're going to have problems later. Think of poor Muhammad Ali. He took a lot of punches in the head, and in his last years, it was Parkinson's, wasn't it? And he, at the 96 Olympics, he lit the torch, and it was pretty sad. Okay, so protective plastic barrels on the highways. Let's think back about cars. What is your protection against a collision? What are some of the things on a car that help protect you? The bumpers. Okay? Now guess what? Oh yeah, we talked about seatbelts earlier. I'm sorry. We already talked about seatbelts and airbags and stuff. But on the car itself, bumpers. Back when I was a boy child, guess what those bumpers were made of? Metal, chromium. I mean, hard. How were they helping you? They were just trying to do more damage to the other car than you did to our. Yeah, that's all they were there for. Pretty bad situation. Now, what are they today? They're plastic. So they give, they bend, they contort. Some of the bumpers have little. Yes, exactly. What do you call those? Sort of like a shock absorber. That's exactly what it's like. So that can increase that time interval, decreasing your force, doing less stuff. Now, another thing, I went to a math meeting a couple years ago, maybe it was last year, and a guy from Mercedes was there, and he was talking about in the old days, they built the structure of the car very rigid, but the compartment of the car was flexible. So guess what? When you hit something, the compartment compressed on you, the rest of the car wasn't damaged that much or as much. Nowadays, they make the passenger compartment the rigid part and make everything else as flexible as possible. So it'll crinkle, you won't crinkle, okay, any more than you have to, okay? That is the same type deal here. In the old days, bridges and barriers, they were hard concrete or steel or something, and when you hit them, crash, okay? Small time interval, huge force. Nowadays, they have, the things they have along the expressways now, they're on little stanchions, they break easily, the wire in between, there's a lot of give to that so that you increase the time interval, decreasing the force with which you stop your impulse. Now, let's look at impulse from another perspective. This is sort of more on the sports perspective, okay? We've been talking about sports, but any of you baseball players? Okay. When you're swinging for the fences, what's your goal? I know to hit it over the fence, but what is the goal with your bat and the ball? What do they say again? Make contact and maintain contact, follow through, right? Same thing through with golf. Any one of you golfers, you follow through. Tennis, you follow through. You ever see, Serena Williams out there just go,
No.
not very often. Wham! I mean, she's maintaining contact of that racket on the ball as long as possible. Cause why? The force acting over a time interval gives you more change of momentum. That ball is going to change its momentum greater. Now let's go back to baseball. Swinging for the fences, follow through. Keeping the bat on the ball as long as possible, changing its momentum. Force times the time interval. Big change of momentum. But there is a tactical maneuver in baseball that they do sometimes, especially if no outs or one out, and the guy's made it to first. A bunt. And how do you do a bunt? Take that ball, that bat, and just touch the ball, and then you pull it back as quickly as you can. Why? You want to maintain a smaller time interval to have just a very small change of momentum. You don't want that ball going back to the pitcher or the first base or third base. You're going to make an out then, a ground out. But if you can just dribble it down here, very small change of momentum, then with a very small time interval contact, that's what a bunt is. Same thing with a drop shot in tennis. They'll do that, try to get it just over the net and dribble down so they can't hit it back. There's lots of things like that. Does that make sense? That's what impulse is. Change of momentum, force times the time interval. Okay, now here comes this other, let's see, maybe it's on the next slide. Let's see if it is. Yeah, no, not yet. Let's go back. Let's now, we've got what a change of momentum is. Force times the time interval, delta t, is equal to a change of momentum. Okay? This comes up, and I told you earlier, up to now we've been saying the unit for momentum was kilogram meter per second. Kilogram meter per second, right? But here's another unit for momentum. What's the unit for force? Sir Isaac? Sir Isaac, the unit for force.
Yes.
Say again?
Yes. Yes. Forces.
What's our unit for force?
Come on.
Named after Sir Isaac.
Yeah,
Newton! Okay. I'm sorry, I couldn't hear you. And what's your time interval? Usually? Seconds.
Mhm.
So a Newton second is also a unit for momentum. Kilogram meter per second or a Newton second. You can use either one for momentum. Okay? Usually you use Newton seconds for impulse, which is a change of momentum, and just regular momentum, mass times velocity, you would do a kilogram meter per second. But you can use them interchangeably. Okay, so that was impulse. Any questions on that? There is a momentum experiment that's talked about at the top of page 48, the right-hand column. We will do something similar to this in the, not today's lab, but in Tuesday's lab, okay? No, Thursday's lab. We'll do something like that momentum experiment there. All right, moving on to 2.8. Any questions on momentum? All right. 2.8 is forces and circular motion. Now, I can remember again when I was a boy child, okay? One of the things I loved to do was swing something around. It's just, I don't know why that was so much fun, swinging something around. I can remember remarking on the fact that I could have a bucket of water here, okay, and swing it around over my head, knowing that when it's right up there, that water was directly overhead, but it didn't follow me. Why not? If I stopped it like that, yeah, it's going to follow me. But if I was swinging it, and an instant, it was directly overhead, but not dripping on me, why not? What's that?
Moving it fast.
Okay, you're moving it fast enough so it doesn't, and that's because of circular motion. Circular motion is, now if I was moving that around, and it could have been a rock on a string around this way, usually that resulted in a broken window, but yeah, never mind. When you're doing something like that, and it's all going at the same speed, are you accelerating?
Yes.
Why? Changing direction. You're absolutely right. An acceleration is a change of velocity. Velocity is a vector quantity. It could be changing magnitude, but it could be changing direction. And sure enough, circular motion is accelerated motion always, because your direction is always changing. Always changing. Okay? Now, there's a type of acceleration we call that, and it's called centripetal acceleration. Okay? And what James said there about the water in the bucket, you see, when you're moving it around like this, the velocity of the water is in the direction of your motion. So it's not trying to come down, it's going that way because you've got a velocity like that. Okay? But what is the bucket doing? Or let's go back to the string. Let's say you have a rock swirling it around like this. Bad idea. You're bound to hit a window. If there's a window in sight, you're going to hit it, you know. And what happens if you accidentally let go, or let go on purpose, or the string breaks? What does it do? Does it continue going around in a circle? No, it goes straight out. Wherever you release it, it goes straight line motion. Remember Newton's first law? An object in motion tends to stay in motion in straight line unless acted on by an unbalanced force. Well, the string is that unbalanced force. It's always pulling it where? To the center. And that's what centripetal means. You can also see the word center in that. Center seeking is what it says. The center of seeking acceleration is present always pulling the object toward you. Because that water in the bucket is trying to go that way. When it's directly overhead, the bucket is pulling it down. It's not trying to drop down, the bucket's pulling it down, keeping it from going in that straight line direction. So therefore, if there's a centripetal acceleration toward the center, there also has to be a centripetal force toward the center. Now, some people talk about a centrifugal force, which there isn't really such a thing. That's sort of an imaginary thing. It's sort of a made-up thing. It's the apparent outward tug in the direction of changes. Like you're in that bus seat or the car seat, and someone turns all of a sudden, you say you're thrown into the door. No, you're not. The door cuts in front of you. You're trying to maintain a straight line. It cuts in front of you. It feels like you're being thrown out, but really not. You are trying to follow straight line motion. That's the apparent, not real, but the apparent tug in the direction as the direction changes. So your centripetal force, when it ends, like the stream breaks, then the motion continues in a straight line. Okay? Here's sort of an illustration of this. If you have the ball on the stream here, okay, and you're twirling it around, the radius, the stream is pulling the ball inward. The velocity is trying to take it parallel, tangential to the motion here, but the stream keeps pulling it toward the center, and that's the center-seeking or centripetal force. Okay? What else depends on this? What are we doing right now? We, the Earth. Name a few things we're doing. What's that?
Rotating.
We're rotating, that's for sure. What else are we doing?
Spinning.
Second?
Spinning.
Spinning, that's what we mean by rotating. Okay, and what's the other that you were thinking of? Going around the sun. Okay, that's centripetal motion. We're going this way, but the gravity of the sun keeps pulling us in. If it weren't for that, we'd be heading to outer space and getting very cold very quickly. You could soon be dead. Okay? Thank you, sun, for pulling us in and keeping us almost centered about the sun. Okay? Lots of activity uses this centripetal force. Okay. With these concepts in mind, let's come up with the formula for a centripetal force. Ooh, they missed it. Okay? I'll have to write it in. Okay? It's on page 49. First column. First, the centripetal acceleration. That's called A. This thing always gives way when I'm trying to write. Let me clean that up a little bit. All right. AC, that's the centripetal acceleration, in terms of these things we have here, is V squared over R. Your velocity squared divided by the radius. Okay? Now, that's not our normal units for acceleration, is it? What would be our normal units for acceleration? Units? Just give me typical units. What did you have in lab? Acceleration. What was the units for acceleration?
We had mass.
Okay, we're not talking about mass yet.
We had
Acceleration.
acceleration. We had
Velocity.
Change of velocity
We
per
had
unit time, that would be meters per second, that's change of velocity per second. So meters per second squared, feet per second squared, miles per hour per second, something like that. Distance per time per time. Well, this doesn't look like that would give it to us, would it? Well, let's see, velocity would be in, you want to use meters? That would be meters per second, but you're going to square that, divide it by radius. Radius would be measured in meters. Well, this will give you meters squared per second squared, that's velocity squared, divided by meters. Well, this meter cancels one of those out, and guess what we've got? Meters per second squared. That does give you your standard unit for acceleration. Velocity squared over radius, that gives you your centripetal acceleration. Okay? Now with that in mind, your centripetal force, be F sub c, that would be your mass times your centripetal acceleration, and that would be mv squared over r. So that's how you get centripetal force. That would be rock on a string, water in the bucket. That's also what they have at Talladega, right? You're going around those curves. The force has to be pushing you in, otherwise you're through the fence and over into the crowd, and not very good deal at all. You have to have a force pushing you in. Part of that force is the bank. Your normal force of the bank is pushing you inward. Okay? All right, finally had a X chromosome show up. Good to see. Okay. Lakeisha, right?
Yes, sir.
Okay. I was trying to find you here. There you are. Okay. Boy, it's gotten ugly for a while, all these Y chromosomes. Never mind. Okay. So, that gives you your centripetal acceleration and centripetal force. The bank at Talladega or on the expressway. Any road around the curve better have a bank to it, otherwise you go into the ditch. Okay? All right. Let's look at example 2.16. Now, I need to get, here we go. We'll do it right here. A 0.25 kilogram ball. 0.25 kilogram ball. What's that a measure of? Mass. That's the mass of the ball. Okay? Is attached to the end of a 0.5 meter string. What would that be in this picture that we had right here? What would that be? That's your radius, exactly. There's your radius, okay? And moved in a horizontal circle at 2.0 meters per second. What's that a measure of?
Velocity.
Velocity. So there's your velocity, okay? The question is, what net force, so we're looking for net force, would you have to keep the ball in a circular path? What was that formula? Mass times velocity squared divided by radius. Plug and chug here. Mass is 0.25 kilograms. Velocity is 2.0 meters per second, but you're squaring that, squared, divided by 0.5 meters, right? That's the length of your string. Now, when you're doing a problem like this, what do you do first? You do the squaring first. Remember the little rule? Please excuse my dear Aunt Sally. The please is parentheses. Well, the parentheses is just enclosing the numbers. The next thing is the exponent. Excuse is the exponent. So you square first. So this will be 0.25 kilograms times 2 squared is 4.0, and you square the units as well, meter squared per second squared, divided by 0.5 meters. Okay? Now, how you approach this, it's up to you. When I see 0.25, what fraction do I think of? A quarter. And a quarter of 4 is? Or 0.25 times 4 is? Yeah, a quarter of 4. 1, exactly. So this goes to 1. So now you have 1 kilogram meter squared per second squared divided by 0.5. Okay, you can either take your calculator and do 1 divided by 0.5. What do you get? Do you know? 1 divided by 0.5? Do you say 2? Yes, exactly. That would be 2.0. Whoa. Is it 0.0? Nope, only 2. 2. And what units? Kilogram. And this meter cancels one of those meters out. Meter per second squared. What's a kilogram meter per second squared? Kilogram meter per second squared? Sir Isaac? Newton. That would be 2 newtons. That is a good unit for force, 2 newtons. And that's sure enough what they got in their calculation as well. Now, the next question said, 2.17, suppose you make the string in example 2.16 1/2 as long, or 0.025 meters. So now we're going to do a different one. Let's do this in a different color. What color you want this to be? Oh, give me one. Huh? Purple? Okay, there's a purple. Okay. So this time we're going to have a new force. Okay. And this new force, let's see. Everything else stays the same. So the mass is still 0.25 kilograms. The speed is still the same, 2.0 meters per second. But you square that, but now you make the string half as long. So that's 0.25 meters. What do you reckon that does to your force? Increase it or decrease it? Increase it, and why? Because these are inversely proportional. You lower this, so you're going to increase that. Exactly. And what does it become then? Well, now here it's pretty obvious that you can cancel out the 0.25, and 2 squared is? Second? 4. Okay. 6, 8. Who do we appreciate? All right, good. So 4 points, or let's just call it 4 kilogram meter, okay, per second squared, which is 4 newtons. So yes, you half the string, you double the force. And you know that's true probably, don't you? If you're swinging something with a shorter thing, you have to exert a lot more force to keep it from flying out there. So sure enough, that's true. That's a lot the same way. Have you seen those figure skaters when they do their spins? If they have their arms out like this, they sort of spin closely. What happens when they pull them in? They look like they're going to drill through the ice there, don't they? Okay. That's it. Okay. Good deal. Any questions? Forces in circular motion. We're ready now for 2.9, which is Newton's law of gravitation. Man, this guy did so much, didn't he? 3 laws of motion, gravitation, he did light, he did chemistry, he did, goodness, there wasn't much he didn't. Oh, he developed a whole new language of math, calculus. Didn't exist before him. He did it all. Man, what a guy. Newton's law of gravitation. By the way, good paper topic. Hint, good paper topic. Hint, hint. Okay. Don't forget your papers, folks. Guess what yesterday was? Last day in October. So that means December, this is November. I only get 1 bonus point from now on until the 1st of December, when you get 0 bonus points. So if you want a bonus point, get it in this month. Sooner the better, if you do. Yeah. I got it written down. Okay. All right. Newton's law of gravitation. Any 2 masses you happen to have, they're attracted to each other by gravity. Now, do I feel any real attraction to that desk? Not particularly, because I'm just too far away to feel it. But even if I got real close to it, I don't feel any. because it's very small. It's a very weak force. We mentioned this at the very, very beginning. But if you have enough mass, as in the mass of the sun, that's a lot of mass. And the mass of the earth, that's a whole lot of mass there too, then they feel the attraction due to gravity. Or earth and moon. That's why the moon goes around the earth, because of the force due to gravity. But it depends on, it's always an attractive force. Now, in electricity, which we'll do in a couple chapters, there's repulsive forces and attractive forces. Like charges repel each other, unlike attract each other. In magnets, like poles repel each other, unlike poles attract each other. But in gravity, it's all toward the center. Okay? It's attractive force between any two masses, or if you got more than two masses, all the masses. It's what keeps, do you know what galaxy we're in? The Milky Way. It's what keeps us in the galaxy, because all that mass of all those stars, and there's a huge black hole in the middle that is really, really, really massive, that keeps us all spinning around the center. Just like we spin around the earth, the sun, and the moon spins around us, all the stars in the Milky Way spin around the center. Okay? That's the attractive force between all masses. Now, it's proportional to the product of the masses. Mass 1 times mass 2, the force is proportional to that. However, it's inversely proportional to the separation distance between. That's why there's less attraction between me and the desk now than there is there, than there is there. The closer I get, the greater the force. Of course, it's still not very great. It's really, really small. Okay? Inversely proportional to the separation distance squared. Not just the distance squared. Now, this also tells us where we get that 9.8 meters per second squared. We'll show that in just a couple of minutes. Okay? And this provides the force for centripetal motion. That's why we say orbiting around the sun. Okay? So here we have it. This is the moon and the earth. The earth has an enormous mass. The moon has a pretty good sized mass. And the interaction between those two, the earth is always pulling the moon toward it. That's what keeps it in a circular path. If that wasn't strong enough, the moon just goes straight on out there. But it is strong enough and pulls it in. Okay? Now, if you, hopefully this will never happen, but if, say, an asteroid or something else came and hit the moon and knocked it closer to the earth, then it's going to probably spiral down and crash into us. Don't want that to happen. Now, if something were to hit it and knock it away from us, then more than likely we lose our moon. Okay? It just depends on how much additional velocity it has and stuff like that. Right now, it's sitting in a pretty equilibrium state. It's going to stay spinning around us. Now, the interesting thing is, the first half of this course, and I know that Nick remembers this, the astronomy and earth science part, they actually think our moon is there because it got knocked off the earth. That some big collision happened a long, 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 long time ago and knocked part of the earth out, and that part is the moon. Okay? And a couple of things that contribute to this. Do you know what side of the moon we see? Only one side. When it's here, we see that side. When it's over here, it acts like it's still part of us. It doesn't. We never see the back side of the moon, ever. Second?
So it's on the dark side of the moon.
Yeah, yeah. Now the dark side, it does get dark on that side and light on the other, but that happens. But yeah, I know what you're talking about. It's science fiction story. Yeah, but you never see the back side of the moon. Now that we've been up there around it, they've taken pictures of it. But really, the moon acts like it was part of the Earth, and they think it probably was. All right, this is Patrick. All right, good deal. Slowly getting a good-sized class here. Okay. So, This describes gravity. Newton came up with this. Now, you've heard the story of how he came up with it, right? In fact, it's a pretty incredible story all the way around. Isaac Newton's father was also an Isaac Newton, but he died before little Isaac was born. He died in the couple months before he was born. So Isaac Newton never knew his father, ever. Okay. His mother later remarried, and he was a sickly child. He was a premature child. For all rights and purposes, he never should have lived. I mean, he was too young, and they didn't have the medical facilities back then, but somehow he did live. Okay, thank you very much that he lived. Okay, but he did live. His mom later remarried and had children by her new husband, and they didn't really take to Isaac too well. He probably was a little difficult child, I don't know. But anyway, he was sent off to live with his grandmother or somebody else. So he had trouble with separation, anxieties, and things like this. He never married, by the way. But something unusual, well, ultimately I think his stepfather died too, and he went back to live with his mom again, and I think by this time they had a farm, so she wanted to pull him out of school. What was school going to do for him anyway? Okay, and try to make a farmer out of it. From what I understand, he was a pretty lousy farmer, okay, because he sat around thinking all the time and not really doing too much. And supposedly he was sitting under the apple tree watching the apple fall and saying, you know, why did it fall? You know, and he started developing in his little active mind this whole concept of the law of gravitation. No one had ever thought of it before. Why? I don't know, but they hadn't. He thought of it. Now, he had an uncle, I believe it was, or someone who saw really how bright this kid was. I mean, didn't do all that well in school because he was pretty bored with it, but this guy said, you know, I think it was his mother's brother, said, you really need to send this kid to Cambridge, you know, and let him go to school. And I think he provided some of the money and sent him off. Now, he was poor, really, really dirt poor, lost two dads, you know, and didn't have much going for him. He worked for the other students, like shining their shoes, bringing their food, washing their clothes and stuff like this to afford his own tuition to college, okay? Pretty rough, okay? And yet he was brighter than all of them put together. I mean, so this was probably pretty tough. But shortly after he graduated, I mean, in just a couple years, he knew more than his professors did. I mean, he absorbed everything they had to give him and went beyond that. He read books, he read things. None of them could keep up with him. Finally, one of the guys said, look, I'll resign so you can take over my chair and have a place here on the faculty. And he did. But, you know, if being on a faculty, you got a lot of committees and you got all this other stuff to do and teaching and all this kind of stuff. As it turned out, he probably wouldn't have gotten a lot done scientifically. I mean, he was a bright guy, but he had all these responsibilities. But the strange thing happened. Anyone know what the plague is? Okay, bubonic plague. They called it the Black Death. I mean, when it came and hit, people died by the wagonfuls. I mean, they didn't know what caused it. Now they do. Anyone know what caused it? Fleas. Yeah, fleas biting the animals, and the animals then biting the people. The fleas biting the people, and you got these germs that bodies we couldn't handle. They killed us. Didn't kill the animals, it killed us. Okay. Well, the plague broke out, and they broke out in the cities. They had really lousy sanitation, so the mess just ran down the gutters and into the thing. So the rats were big and nasty and flea and stuff like this. So anywhere there was big concentration of people, the plague, I mean, it just flourished. So when they saw the plague coming, they had the best and the brightest minds at the university. they said, look, send them home or they're all going to die. Okay? So they did send them home for about 2 years. So he had to go back to the farm for a couple years. By this time, he had all this knowledge. So while he was home, he wrote all these books. He came up with these laws. He did all this kind of stuff because he had time to do it. He didn't have all these other distractions at the university. By the way, the plague was known for several things. When you got it, you got a rash that usually went around your neck. Just bright red, burning hot, your fever and stuff like this, and in a few days you're going to be dead. They came up with a little nursery rhyme that related to that. Does anyone know what it was? Ring around the roses, the red rash around here, pocket full of posies. What are those? They were flowers. They had a real sweet smell because when the plague hit, the stink of death was just terrible, and people would take the flowers and hold them to the nose. A pocket full of posies, ashes, ashes. They had to burn the body. They didn't have time to bury them. Ashes, ashes, we all fall down. When your kids are playing that song, they're playing about the plague, the bubonic plague, and death is what they're singing about. Yeah, but that's beside the point. But it was.
They had the bird mask.
What's that?
You know why they had the bird mask? Like long 20.
Why is that?
They set the roses in the
Oh.
mask so they wouldn't smell.
Yes,
That's why
exactly.
doctors had the plague mask.
Yeah. Yeah, it was. Had to have been awful. But if it hadn't been for the plague, we wouldn't have had the 3 laws of motion. We wouldn't have had the law of gravitation. We wouldn't have understood optics. So sometimes things do. Even bad things work out for good sometimes. Okay. All right. Oh, we didn't get the formula. Let's see if they're going to give us the formula. No, they're not. Okay, so let's do the formula. From what they tell us here, the force, attractive force of all masses, there's a force. Oh, you want to stay in purple or go back to black? Okay, let's go back to black. Okay. Second. Okay. The force due to gravity, okay, is proportional to, remember our proportional sign? Proportional to the product of the masses, M1, M2, that could be Earth and Moon or Earth and Sun or whatever, proportional to the product of the masses, inversely proportional to the separation distance between. So if this distance here is r, that would be divided by r squared. Inversely proportional to the distance squared. Okay? Now, we need to make that from a proportionality to an equality. What we do then, the force due to gravity, is equal to some constant, we'll call it G, universal gravitational constant, M1, M2, divided by r squared. Okay? Now, that's the equation that you find on page 50 near the top of the first column. F is equal to G, M1, M2 divided by, they put D squared, I put R squared. What's that? D. That's distance squared or radius squared, whichever you want to call it. Okay? It's just a symbol. Right. Now, that constant G is a universal constant. It doesn't have to do with the Earth. It doesn't have to do with the Sun, the Moon, or anything else. It's universal throughout the universe. Okay? It works. It was first measured experimentally by Henry Cavendish in 1798. Now that's interesting because I think Isaac Newton lived about the 1400s or so. So it was about 300 years later, maybe 350 years later, before they ever figured out what that constant was. Newton knew it was a constant, he just didn't know what it was. So he got that. It's the accepted value today, and here's why I don't feel any attraction to this desk. Because look at this constant. That G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Whoa! What's 10 to the minus 11? That would be a 0.000000667. That is a tiny, tiny, tiny number, so I'm not going to feel any attraction to the desk, especially since our masses are so small. But when you get masses big enough to be like the Earth and the Sun, or the Earth and the Moon, then those masses are big enough that you can feel that force due to gravity. Okay? So that's your formula. Let's do example 2.18. What is the force of gravitational attraction between two 60-kilogram students? That's about 132 pounds. Some of you might be close to that. I haven't been close to that in many decades, but maybe at one time in my very early life I was 60 kilograms. But they're standing 1 meter apart. So let's see what the force due to gravity would be with them. So I'm going to take this formula and plug in what we've got here. We're going to use that value for G, so let's do it. Okay? The force due to gravity between these two 60-kilogram students. The gravitational constant is 6.67 times 10 to the minus 11. That would be Newton meter squared per kilogram squared, multiplied by mass 1 was 60.0 kilograms. Mass 2 was also 60.0 kilograms. Okay? Divided by, they're standing 1 meter apart. So that would be 1.00 meters squared, because you're going to square that distance. Okay?
And you squared it because you got two of them, right?
Well, it's because it's d squared or r squared.
Okay.
Right. Okay? Now, let's first take a look at the units. Here we have meters squared here, and here we have a meter squared up there. They cancel out. Here we have a kilogram squared, and here you have a kilogram times a kilogram. They cancel out. So that leaves us just with newtons, which is a very, very good unit for force. Okay? Now, if you got, do y'all know how to do scientific notation on your calculator?
Yeah.
Okay. So you do 6.67, and then find a key that says something like EE or EXP. So 6.67, press that key, and then type in a negative 11. Some of the older calculators, the 1 with the minus, plus, minus. Others, you do the minus sign and then do the 11. You have to know your own calculator to do how to do it. Then multiply that by 60, multiply it by 60 again, and then what's 1 squared? It's 1. Divide by 1. What do you get? Yeah, 60 times 60. 0. Okay, give me those zeros again. 1, 2,
6 zeros, I believe.
2, 4. And that would be newtons. All right, let's see what that you would measure that as. That's 24 millionths of a newton. Okay? I don't think I'm going to feel much. Okay?
No.
That force is so terribly tiny. Let's see what they got. They said it this way, 2.40 times 10 to the minus 7. So move this 1, 2, 3, 4, 5, 6, 7. Oops. I don't think you said enough zeros. There was one more zero in there. Okay. So that would be 2.40 times 10 to the negative 7 newtons. That's 24 millionths of a newton. Not noticeable. Okay, not measurable. Okay. Now, okay. Now, there is another thing we can do with this. All right? You remember what the force due to gravity was?
Force.
Yeah, force due to gravity. In other words, weight. The weight, which is force due to gravity. Remember what we called that earlier? mg. Remember that? Okay. Well, the m is one of these m's. So let's take the rest of what we've got here, and since we're talking about force due to gravity, that's gravity of the Earth. So let's go now. If you got the big books, you can look this up. If you don't, you're going to have to take my word for it. But at the front inside cover of your book, you have these physical constants. Now, the little books don't have them, but if you have the big books, you got them. Okay?
Equals 9.8.
Okay, yeah. We're going to see if we can get that. Okay? And how we're going to do this? We're going to multiply these units by each other. This is going to be your mass, M1. The other mass is going to be the mass of the Earth. Okay? So let's do that calculation. The G is 6.67 times 10 to the negative 11, and that will be, I'll put it as Newton meter squared per kilogram squared. Kilogram squared, okay? That's your universal gravitational constant. Multiply that, and like I said, that second m is the mass of the Earth. And the Earth's mass is 5.97 times 10 to the 24th, 10 to the 24th kilograms. Whoa! That would be 5,970,000,000,000,000,000,000,000. I mean, you got 8 sets of those 3 zeros there. That's a huge number. That's a huge mass. That's the mass of the Earth. Okay? And we're going to divide that, though, by r squared. Well, r is the radius of the Earth. So the Earth mean radius is 6.38 times 10 to the 6th meters. So that's 6,380,000 meters. Okay? That's a lot. But then we're going to square that. Remember, it's r squared. Okay? So if you got your calculators, okay, here's what you punch in. 6.67 EE or EXP, whatever key your calculator has, then minus 11, however you do that for the exponent, times 5.97 EE or EXP, 24, okay, divided by 6.38 EE or EXP 6, but then square that number and then hit your equal sign. Yeah.
9.78.
Oh, wow. What did you say?
9.78.
9.78 on the nose, right? And guess what that is? That's your acceleration due to gravity. Let's see if we get that. This Newton, by the way, is a kilogram meter per second squared, multiplied by another meter squared. Well, this meter squared is going to take out this meter squared, so that's out of there. One of these kilograms is going to go out. The other kilogram is going to go out here. And what are you left with? A meter per second squared. Meter per second squared. What does that round to? 9.8 meter per second squared. That's where you get the acceleration due to gravity. You got 9.78, that rounds to 9.8 meters per second squared. That's where it came from. All from the constants of nature. You didn't make up anything there. It was all that. Now, of course, if you were on a different planet, like Jupiter, then your mass is going to be a lot bigger, but your distance from the center is going to be a whole lot bigger, so it's going to change. If you're on Venus, that's going to be very similar to Earth, probably a little bit less. If you're on the Moon, it's much smaller than the Earth. Okay, so that's why the acceleration due to gravity changes according to where you are. On the surface of the Earth, it's constant. Anywhere else in the universe, it's going to be different. Okay, and I lost my place. Okay, I can find it back. So this is Newton's law of gravitation. Okay. Oh, and by the way, guess what? That was example 2.19. I was looking at it over here on page 50. I realized it's over here on 51. So we've already done it.
Okay.
Done. Now, we're going to change it though. Okay? All right? There's the plug if you want to plug it in there.
I'm running low.
Okay. You're welcome to sit there if you want to. But,
Will it be if I just stand for a second?
Oh, it don't bother me at all. I understand the feeling. That's why I like to teach. I get to walk around and stand, you know. Okay. Let's do 2.20. Okay. We're going to use a lot of the same thing that we did have, but we're going to, what would it be the value of G if the Earth were less dense with the same mass but double the radius? Okay? So what we're going to do here, we're through with this problem here, so we're going to get rid of it. Okay? Okay, and we're going to get rid of this. That was the other problem. Okay. This time, what we're going to do is double the radius. If I can get that to erase, it won't erase. Oh, that's on the slide. Sorry about that. Okay, duh. Okay. So if you double the radius was, there it is, 6.4 times 10 to the 6th meters. So let's make it 12.8 times 10 to the 6 meters. Okay? So we're going to plug in everything just like it was, except the radius is doubled. So again, you do 6.67 EE or EXP minus 11 times 5.97 EE or EXP 24 divided by, but this time it's 12.8 EE or EXP 6, but then square that and then press equal sign.
Times out the 5.97 to 24 times,
Yeah. Then divided by 12.8 EE or EXP 6, but then square that number and then enter equal sign.
Wow.
What you get?
2.4.
2.4. Now the gravitation of the Earth would be 2.4 meters per second squared. Our acceleration due to gravity would be 1/4 of what it was because we doubled the radius, but then we squared it. So that's reducing it by a factor of 4. So then I'd be able to jump, okay? Yeah, because,
Yes.
the acceleration due to gravity would be so much less. 1/4 what it is now. 2.4 meters per second squared. All right. Let's move on to Earth satellites. Okay? We talked a little bit about this earlier, but this is an example of centripetal forces, acceleration, that kind of stuff. Artificial satellites must travel more than 320 kilometers above the Earth. If they're less than that, they're going to fall down. Okay? There's nothing to keep them up there. So they've got to be more than 320 kilometers above the Earth. Now, what is that in miles? That would be about 200 miles above the Earth's surface. Okay. Now, But also, they must travel at least 8 kilometers per second to maintain orbit. If they're not going, and that's 8 kilometers per second. That would be almost 5 miles per second. 5 miles per second. They have to be going that fast of speed. Okay. Now, I think we mentioned this before. We have all these satellites up there, and they do different things for us. Some of them send us our television signals. If you have Dish TV or Direct TV or some of those, that dish is up there pointing in one direction, always toward the satellite. That satellite is beaming down to it. If it weren't stationary, you'd only get that signal maybe once a day, and maybe not even then. So those are called geosynchronous orbits. But those aren't the only ones that are in geosynchronous orbits. Any of your GPS satellites, and you have to have a bunch of them up there. Yeah, because if they weren't stationary, you wouldn't be able to tell where you were. They have to be fixed above the Earth, so when the Earth turns, they turn right with it. Sort of like, not quite like the moon does, but sort of like that, okay? And you have to have at least 3 of them to tell you where you are. Because if you were out here, this looks like you're probably near the middle of the Atlantic Ocean. Okay, there's Greenland, there's North America over here, here's Africa, Spain, Europe, England. So you're out in the middle of the Atlantic Ocean here, and you want to know where you are, and you don't have a sextant and other things like that, but you have your GPS thing, and you can get a signal. If you had this satellite here, all that tells you you're somewhere on this circle here, because you know where that satellite is, and you know just enough about it to know you're on that circle. Well, with this satellite, you know you're on this circle. Well, then you know you're either here or there. That would put you off the coast of Iceland. This has you back down here. So you need at least a 3rd satellite to tell you're on this circle, and now that tells you you're right there. Yeah. Well, pretty close. Yeah. The military, they can really get you down. They say they can tell with their satellites, they can almost read a license plate. I mean, they are that good. We don't get that kind of signal, okay? But we do get pretty good signal there, okay? But you always have to have at least 3. They probably get more than 3, and they pick out the best 3, the strongest 3, and that usually gives you a pretty good idea of where you are, okay? I think they usually say you're within, 100 meters or something like that. I don't know for sure. Some of y'all take Mr. Perry's course. You have. How good is GPS? How close does it get you? Does he tell?
Yeah, he did. I think he did somewhere like that.
Yeah. 50 meters, 100 meters, 10 meters, something like that. Okay. The military, they get you down within, so they can guide those smart bombs right in there. Okay. Now, we talk about weightlessness. That really isn't quite true. Astronauts appear to be weightless, but they're still affected by weight because they're never that far from the Earth. You can still see the Earth behind them there. They are still being pulled toward the Earth. In fact, if they weren't, they'd be flying off into space, okay? So they are still being pulled down, but it's just like the moon going around the Earth. It's being pulled toward the Earth, but it doesn't fall to the Earth, okay? So therefore, they can't be weightless because they are still traveling around the Earth. The astronauts are actually in constant free fall, falling toward the center of the Earth. But because they have a velocity this way, like 8 kilometers per second, they don't go toward the Earth. Now, when they're out there, this I guess is a space station or something like that. If they were to push off from the space station and weren't tethered to it and didn't have retro rockets, if they happen to have those, they would never get back to it. You have to have something, because once you do, there's not anything to slow you down. You just keep moving away. So they usually are tethered, or they have some sort of rockets to it. Probably not. There's not much of the Earth's atmosphere. It falls off really quickly as you go up. There's probably very, very slight traces of it, but not enough debris. Okay? And that leads to another point. These big old heavy suits there, why do they have those on? Okay, yeah, there's several reasons. Number one, they have to have all their source of oxygen within that because there's nothing out here for them to breathe. That's number one. Notice what color they are. What would you call that?
No.
Very reflective. They're usually silvery or white. That looks whitish, but I bet you it's really silvery. Why would they want to be reflective like that?
Keeps the sun from.
Oh, you got it. Because out here in space, you see our atmosphere, thank you atmosphere, it prevents most of the deadly radiation from ever reaching the surface of the Earth. And I mean, there's plenty of deadly radiation out there. Gamma radiation, cosmic radiation, I mean, there's tons of it. If it weren't for our atmosphere, we'd be toast. Okay? Wouldn't make it. Okay? So they have to have these on to reflect that deadly radiation away from them. Big time. Okay? They don't have the atmosphere around them. So they have to have their supply of oxygen inside. They have to have them to reflect that radiation. But the other thing they need is pressure. These are pressurized. Now that's part of the oxygen that's in there, but it's pressurized. Do you know what normal atmospheric pressure is?
Listen.
If I gave you the units, PSI, what would it be?
No.
14.7 PSI. What does PSI stand for? Pounds per square inch. Now, a square inch is about your two thumbs put together like that. Okay? Now, think about how many square inches there are on your body. Multiply it by 15, 14.7. That's a lot of weight. That would be how many pounds of atmosphere pressure is pushing down on you every second, all the time. Okay? Why aren't we crushed? Because we've got pressure inside our body pushing out. They call it turgor pressure. Now my mom, turgor, that's what my mom used to call it. She used to do this and make me feel really bad. Now I can do it and I feel even worse. If I take the skin on my hand and pull it up like that, it takes a little while before it flattens back out. You young folks, it probably does it immediately, right? I don't want to see it, okay? She used to do that, and it would stand there like a tent for quite a while before it finally went back down. The older we get, we have a little less pressure inside, okay? So here we have 14.7, probably like 15 pounds per square inch pressure pushing out on us. Okay, up here, how much pressure has he got pushing in on it? Almost nothing. And if he has 15 pounds per square inch pushing out, if he were to rip that suit, yes, all the blood and the gases from his body go probably first out of the eyeballs, the ears, and everything. I mean, dead in an instant. If the radiation wouldn't kill him, it wouldn't have time because he goes spewing out of that. Now think about this. I remember way back before the current space station, we were using the Soviet space station. This is back when they were Soviet Union. It was called Soyuz, S-O-Y-U-Z or something like that. And they used to send up these unmanned rockets, you know, and stuff to resupply the cosmonauts who were up there on their space station. Well, one of them hit the station too hard and damaged it, and those cosmonauts had to go into a tiny little area and live there for a long time. I mean, just crammed in a very small space until we were able to send our space shuttle up there with enough stuff to repair. And those astronauts and cosmonauts were out there where metal that was all bent and twisted and sharp and jagged, and they were working on this, trying to repair that. That had to have been one of the most dangerous missions ever attempted by man, because any little rip on that spaceship, dead in an instant, okay? Had to be incredible, but that's beside the point. We're not talking about that now. I was, but that's just beside the point. Okay, good deal. There's weightlessness. They're really not weightless, but it's very, very small weight compared to what it would be on the Earth. That, folks, is the end of the chapter. Now, there's a few more things here I want to point out to you. One of these is gravity problems, okay? That's the little bluish blurb at the top of page 53 or somewhere thereabout. It's well worth a read, folks. Well worth a read. And then here we get good old Isaac Newton. I gave the dates wrong. He was 1642 to 1727. And remember, Cavendish was 1798. So that was more like 3/4 of a century after Newton died. Cavendish finally determined what that G was. So there's Isaac Newton. Now, if you choose to write on Newton, guess what? This is not your source. This may give you some ideas, but you have to get your sources from the library or the internet, somewhere else, not the book. And much of what I said you can read here, and a bit more too. I was trying to think. They mention a couple of other guys here. There's Edmund Halley, friend of Newton. He did quite some interesting thing. You've heard of something named after him, I bet.
Say that name again.
Edmund Halley.
Halley.
Yes. Had a comet named after him. Halley's Comet. Goes around the Earth about once every 75 years. You get to see it. It's already happened in my lifetime. You won't get to see it again, I don't think, okay? Maybe you very young people might, but not me, okay? So that would be another potential paper topic. If you read on a little bit further, you notice they mention him with Archimedes and Albert Einstein, 3 of the greatest minds they think that ever lived, okay? So, anyway. Then there's a thing on apparent weightlessness, and here is Wayne, right?
Yes, sir.
Okay. I think Nick picked up your last lab for you, okay? It hasn't been filled in, but you have to get it from him.
All right.
But we're going to do another lab today. Yes?
I didn't get the lab. Is that it?
What's that?
The lab from last week.
Yeah. You need a copy of it? Okay. Okay. Much shorter than the first one.
Okay.
Okay. All right. So, many potential paper topics there. Nothing, I say this every chapter, and I'll say it every chapter from now on, nothing replaces reading the chapter. Please read the chapter. Once you've read it, though, the summary is half a page. The chapter was probably 30 pages, okay? So it can't catch it all, but it catches a lot of the important things on the summary. Then this chapter, wow, 12, I believe it is, summary of equations. If I were you taking the next test, I'd make sure I had at least those on that piece of paper. You know you do get to bring a piece of paper to the test.
And which one is that? That's the for what now? The chapter 2.
You can write down anything you want on the piece of paper, but I would make sure you had those 12 equations on it. And then anything else you want to write down. But that's up to you. You choose.
Well, the 12 equations there.
They're on the right-hand side of page 55, or 11 of them. You turn to the top of 56, there's one more.
Oh,
Summary of equations, exactly. Okay? Then there's key terms. These are pretty important too. Now they give them alphabetically, but they do give the page numbers, so you can look them up if you don't know where they are. But another really good thing to do to study for the test is applying the concepts. That's pages 56, 57, and 58. There's 47 questions there, all multiple choice, You're not going to see exactly these questions on the test, but you're going to see some questions that are similar, certainly that are covering the same material, but just asked in a different way. So if you can do those 47 questions, they have the answers given. You see if what you think the answers are, compare them to what the answers are, figure out why you're wrong. If you have any uncertainty, I don't know why I missed this, ask me, okay? So next class or later today, whatever. Another good thing to look at is questions for thought. There's 12 of those on page 59. There's another 6 for further analysis. All those are well worth thinking through. You don't have to write them down if you don't want to, but I would definitely think through those. There's an interesting little invitation to inquiry. That's up to you whether you want to do that. And then there's some parallel exercises. Now, and these are Group A, Group B. It doesn't matter which ones you do. If you happen to have the big book, the Group A answers are in the back. If you have a little thin book, they didn't put the answers in. Sorry about that. But I'll be glad to copy the answers for you if you want them. Okay? But Group B doesn't have them, but Group A does. And there's 31 of those. Now, you don't have to do them all, but these use those equations that you saw. So these would probably be a very good thing to study. Okay? Now, that's it for Chapter 2. And I told this to the others, but if you came in late, you probably didn't get to hear it. At 5:45 today, we will stop and have our second lab on Chapter 2. It's called projectile motion. Okay? It's our third lab, but it's the second one on Chapter 2. We're going to, for the rest of the class period today, and it's now 5:11, so for about the next 30 minutes, we're going to get started on Chapter 3. Okay? Then on Thursday, we're going to start back with Chapter 3, pick up where we left off, and then at 5:15, we'll stop and have the third lab from Chapter 2. Okay? Then, you'll be finished with that by 7:15, maybe earlier. I think it'll be earlier, and then you can do your test on Chapter 2. So that's when you need to have your formula and equation sheet ready. Scratch paper, yeah. This coming Thursday, day after tomorrow.
Okay.
Day after tomorrow. Okay. So we'll have the second lab on Chapter 2 today. We'll start in about 30 minutes. We'll have the third lab on Thursday at 5:15, and then the last 30 minutes you'll have your test. Now, you'll probably finish the lab early so you can start your test early. When you finish your test, you can go. Okay? That will be Thursday. We'll start on Chapter 3 today, continue Chapter 3 on Thursday, and then next Tuesday, we'll have the first lab on Chapter 3. So the labs are going to lag just a little bit, but we'll try to get them in before we get to the test time. All right. Any questions on Chapter 2? All right. Then, if no questions on Chapter 2, let's hit Chapter 3. Again, we only have about 15 minutes. So, 30 minutes to do Chapter 3, and then we'll do the second lab in Chapter 2. All right. Say again? Okay, I'm not hearing well, so I can't hear you. Restroom. Oh, yeah. Y'all want to take a quick break? We're going to have lab in about 30 minutes, so we could. But you want to take it now? Okay. Keep it less than 5 if you can. I'll pause this. All right. Chapter 3 is talking about energy. Let's just stop for a minute. Chapter 1 was basically what is science, looking at the various aspects of science. But then Chapter 2 was basically motion. The first sort of half of the chapter, we described motion. Displacements, distances, speeds, velocities, accelerations, okay? Then we talked about what caused motions. That was sort of this next part. And that was forces. And we looked at Newton's laws, and different types of forces, gravitational force, centripetal force, all that kind of stuff. And then we did a few applications, including those, but also momentum, impulse. So all that was talking about motion. Now we're going to talk about energy. Now, I find if there are any words that are perhaps misused more than other, it's these concepts of energy and things like this, because we almost use the terms interchangeably, and they're not. They're distinctly different. So pay attention to the specific definitions. Here's the core concept, and this is given in your book on page 61. They put it white print on a yellow background so you can hardly see it. Here it's a lot easier. Energy is transformed through working or heating, and the total amount remains constant. That's almost amazing to think about. The total amount of energy always remains constant. You can change the form from one to another to another to another. In fact, here is anyone recognize what this is? A dam, okay? I don't know exactly where it is. I don't think it's listed in the book where this one is. But obviously,
It's a Grand Canyon Dam.
the Grand Canyon Dam on the Colorado River, huh? Okay. See, my book is a different one, so I don't have that on it. The Grand Canyon Dam, okay? Water is backed up behind that dam. Why do they do that? Okay. It's over there because when it falls, it picks up energy. See, it's building energy now behind there. We call that gravitational potential energy. And when you release it, it comes gushing through. That's kinetic energy. That kinetic energy is enough to turn turbines, and the turning of the turbines converts electromagnetic energy into magnetic energy into electrical energy. The electrical energy then are sent through the towers to various places across the thing. And then we'll use that electrical energy and make light, make heat, run our computers, run our other things, cook our food, do all sorts of things for us. And all the time we're using the same energy, but it's changing form from one to another, to another, to another, to another, to another, but we never use it up. Energy is not used up, it's just transferred from one form to another. Working or heating, two ways that we transform energy. Okay? So here's our fundamental law. It's the conservation of energy. We already talked about it in the basic concept that energy is always conserved. What were two other things that have been always conserved we've mentioned? Mass is conserved and momentum is conserved. Okay? Velocities, accelerations, speeds, distances, they're not conserved. Mass, momentum, and total energy. Now, energy has many, 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 many different forms. Individual forms aren't necessarily conserved, but the total energy is. Now, it changes its shape and size and things. Here are the different manifestations of energy. Work is a form of energy. Motion is a form of energy. Position is a form of energy. Radiation is a form of energy. Light, we're thinking of that. Heat is a form of energy, or lack thereof, okay? Chemical energy. What's going on in those little leaves out there in that tree right now?
Changing color.
Okay, yeah, they're changing colors, but in the green ones, what's happening in the green ones? It's hard for it to happen, huh?
Are they dying?
Okay, yeah, when they change color they are, but when they're green, what are they doing out there? Especially if the sun's out. There's not much out now, but it's absorbing what?
Energy?
Okay, they're taking energy from the sun in a process called photosynthesis. That photo means light. Synthesis is to make up. So you're making something from the light. And what those leaves are doing, when you said they're absorbing, they're also, in their leaves, they have little holes you call stomata that air comes in. Okay? That's carbon dioxide. but also oxygen, but mostly carbon dioxide comes in. Water, when we ever have rain, comes up through the roots, and the carbon dioxide combines with the water in the leaves with the heat, and that forms carbohydrates, which are your sugars and your starches. Those are your energy products. And those sugars and starches, that's a maple tree right out there. In the spring, it has these little seeds that come down. You see them fly around some, That's where most of that's going. The oak trees have acorns. The pecan trees have pecans. The walnut trees, walnut. But they're storing their energy, and most of them have large amounts of, especially the nuts. If you look at the contents of nuts, say you have a gram of walnuts or pecans or almonds or something like that, look how much fat is in there. The vast majority is fat, but it's usually pretty good fat. It's not the really bad fat, but that's stored energy. Okay, so that's a chemical process that is storing energy. Photosynthesis. Nuclear energy. What is the plant around here? Is it Wilsonville that's a nuclear power plant, or is that a coal power plant? I can't remember. I get them crossed up. But there are some nuclear plants around. Over near where I grew up in Georgia is a place called Vogel, Plant Vogel. Georgia Power and others own that, and that is opening actually a new reactor fairly soon. Mass itself is a form of energy. Ooh, that's strange, isn't it? But I bet you all know the formula that relates it, don't you? Does the name Albert Einstein ring a bell? What was his famous formula? E equal MC squared. You got it. Let's see what those things stand for. Okay. E is energy equal M. Guess what that stands for? Mass. And what's C squared? Anyone know? What is C? No, the speed of light. The speed of light, which is extraordinarily fast. Like 186,000 miles per second. Okay? Can you imagine anything that fast? Okay? So you take a little bit of mass, multiply it by 186,000 miles a second, but you square that and make it even bigger, and that's how much energy you got. Mass itself is a form of energy. Okay? That's the formula that relates it to us. Okay? What are some of the sources of this energy? Well, what we're using large quantities are your hydrocarbons, which are petroleum in the liquid form, coal in the solid form. That's the vast majority of the energy we're using. Moving water, here in Alabama, we have more of this than most states do because we have all these hydroelectric dams. Smith Lake, Gunnersville Lake. Doesn't Lay Lake have a hydroelectric?
Yes, but they're about to dry right now.
Yeah, they're almost drying up. It's really sad. Okay, but moving water provides us a fair amount, not a lot, but some energy. Nuclear, we're using more and more of this, but now ever since Fukushima, pretty bad news there. And actually before that, 3 Mile Island and also Chernobyl, put a damper on nuclear because there's pretty dangerous stuff. Solar, we're just beginning to scratch the surface in solar. My calculator uses it. Doesn't have to be from the sun, but if I leave this out here in the light long enough, please, or maybe I have to press the button. Yeah, there it comes. These are solar cells right there. That's what's powering this calculator, okay? So light is a source of energy. Well, what do we use it for? How'd you get to school today? Yes, you used that petroleum, didn't you? Okay. But it was gas by the time you used it. How How are we seeing? How are we reading? How are we projecting? Electricity, okay? How is this cooling us, huh? Electricity, okay? And a whole process there. Lighting, everything. We use energy we are energy hogs, okay? If you think about how little energy we used to use in the past compared to how much we waste today, it's pretty incredible. Don't get me off on that yet. Okay. As we said before, and this, by the way, is moving, that was all introduction. 3.1 is the actual beginning of the chapter, and that's work. And the very first thing we said here, one manifestation of energy is work. Okay? And 3.1 is going to deal with that. Now, here's how we define work. It's a product of two entities. One is an applied force, and the second is the parallel distance through which that force acts. Okay? I'm going to push on the chair. That's an applied force. I'm going to push on it for a certain distance. That distance through which I push, force times the distance, that is going to be work. Okay? Now it's the parallel distance. If I were to push down on the chair, am I doing any work?
Yes.
Really? The chair is not moving, is it? Okay? So it has to be a parallel in the same direction. Now if I pull on this way, part of my pull is in this direction, that part's doing work. The part that's pulling upward is doing no work whatsoever. So some forces do work and some do not. It's those that act on a parallel distance through which the force acts. Now, if you take that definition, work is then force times the displacement, or a distance. Let's see what units that would have. What is our unit for work? Force. What is our unit for force? Anyone know? Say again? Newton, exactly. That's in the SI unit. And what is our unit for distance or displacement? Meter. 1 Newton meter is what we call a joule. Okay? Now, notice here, capitalize Newton, N for Newton. Why? Named after somebody. Meter, I didn't capitalize. Why? There's no one named meter. That's just to measure. It's from the French word. But guess what? Joule is capitalized. Why did I do that? Named after James Prescott Joule. We'll talk about him later in the chapter. So a Newton meter is a joule. That's a unit. Now in the U.S. customary, our unit for force is pounds. That's just not named after anybody, so that's just LB. And in the U.S. customary, or British system, foot is the basic unit, not meters. So pound feet or foot pounds, that's our unit of work. Okay? So the distance in meters or feet that you lift something, the force with which you have to exert to lift it, in newtons or pounds, you either get Newton meters, which are joules in the SI unit, or you get foot pounds in the U.S. customary. Okay? Now, I guess that's enough to talk about that. Y'all keep up with the time. When it's 5:45, let me know.
5:37.
Okay, good. Okay. So let's talk. Okay, here's the units of work. And by the way, the same units for energy. Work is just another manifestation of energy. The unit is the joule, Joule. It looks sort of like joule, but it's joule, like a diamond or something, joule, just spelled differently, named after James Prescott Joule, so we capitalize the J. Now, what I was mentioning before, if you can add force to something, but if you don't move it, you're not doing any work. Now, that is contradictory to what we usually think of, okay? I don't know, I'll tell you this little story. It's a continuing saga. You'll hear bits and pieces of it at different times. Let me start it now. When my wife and I were looking at the house where we currently live. We're in a little 2-bedroom bungalow, which was nice, but when we had family come to visit, it was really crowded, especially if very many came to visit. So we started looking for a little bit larger house, and we found one in an area of town my wife loved. It had lots of trees. Our first house had 0 trees except the ones we planted now. Some neighbors had some trees, but it was pretty bare there. But the only negative thing about the house when we looked at it, I said, now Karen, I do like the house, but it was built on a hillside, okay? And the front yard goes down like this, but the backyard goes up like this. I'm exaggerating some. But the house was on sort of a flat piece here. But some previous owner had built an addition on the back of the house. And when they did that, they had to dig into the hill a little bit. So the windows in the back were real squatty because the soil came right up to the bottom of the window, and the windows were very narrow because the soil was covering a lot of that. And the hill still came down. And I said, Karen, we get all this hydraulic pressure, the water running down the hill against the side of the house. Now, I'm sure they built a pretty strong wall, but in time, that's going to give us problems. So we need to do something about that. Another issue is we got soil right up to the wood. And that's a problem in the South. If they use treated lumber, it's going to last a while, but after a while, termites are going to get in it. So we need to separate that. So I said we need to get the water away from the back of the house, and we also need to drop the soil level. And Karen said, good, I wanted a patio anyway.
No.
Oh, that's a lot bigger job than I had in mind. I had just planned on doing the little ditching and berming and digging and stuff, but no, she wanted a patio anyway. So she got out there, and we got some hose, and she said, well, let's run the hose. I kind of like it out here and run across here. Oh my goodness. So I figured the only way to reduce the size of that was to for me to get her to help me dig it. And once I did that, the hose came in a little way, so that was good. But the other issues we ran into were roots. We have big pecan tree here and other trees here, so I kept bringing it in because I didn't want to damage the trees, of course, okay? So I kept it coming in a little bit. But in the process of digging out the patio, and I had a pick, shovel, and a wheelbarrow. Later we got, her dad loaned us his rototiller that helped a little bit. That's what she did, and boy, it beat her to death. But she hung with it, okay? But pick, shovel, and wheelbarrow, digging out the patio. But if you dig very much around here for very deep, what are you going to find? Rocks. Lots of rocks.
Everywhere.
Okay? And we found, I was digging along, I'd found these rocks, various sizes of rock. I could usually get them up. But boy, somewhere near the middle of that patio, I found this huge thing. And I worked on that thing and around that thing for days, digging deeper and prying and, everything. I was sweating and exerting force and but guess what? Was I doing any work? If I didn't move the rock, all that sweating and all the things I was saying, that wasn't contributing anything. No distance, no work. Tell me I wasn't working, okay? You'd have had a fight on your hand, but in the physics sense, if you don't move a distance, you're not doing any work because your formula is force times the distance. If you're zero distance, you're doing zero work. Even if you're doing 3 million pounds of force, if you're not moving a distance, you're doing no work. Okay? We'll continue that story later. Okay? Now, another issue is displacement perpendicular to the applied force is also doing no work. Okay? Let's say that I'm carrying this book, which isn't very big, but across the room here. Okay? Now, what force am I exerting on the book? Can you see my hand? I'm having to push up. But what is the displacement? This one. So guess what? as long as I'm doing this, I'm not doing any work on the book. Because the force is up, but I'm not displaced. Now, I did work to get it off the floor up to here. That's doing work because the force is up, the displacement's up. But when I'm doing this, no work. So when you're carrying those concrete blocks across like this, are you doing work? You're doing some, but not as much as when you're lifting the block. That's working against gravity, moving this way. So displacement perpendicular to the applied force is also doing no work. What's that? 5:45. It is 5:45. Okay. Let's see. We will pick up here next time. This is figure 3.3, and that's where we'll pick up here. Let me erase these other marks so I'll know where to go. Okay. Now, I had said that we would go same lab we did before, and that's where my work study student set it up. But now that I've thought about it, I think we're going to the lab across the hall, which is 202. I mean, 252. We were in 253, which is on this side. We're on the other side, just across the hall from where we were. The setup is in the other, but I'm going to move it across the hall, and that's where we're going to go.
Dr. Fowler, is anyway, my last lab I turned in.
Second lab in Chapter 2, projectile motion, is Experiment 6 on the handout I gave you. 3 kinds of motion: horizontal motion, vertical motion, and then a combination which we call projectile motion. We'll be doing some measurements on horizontal today. And by the way, I'm going to pause this a minute. I forgot something. All right. Now, what we're going to do, you notice the setup here. I'm going to tell you a little bit of a modification on what's here, but it's not a major one. Okay? What you're going to do, and I've already set this up for you, so each of these ramps is exactly 1 meter from the edge of the desk, of the tabletop, right? Oh, that's a meter. That's a meter. That's a meter, and that's a meter, okay? So you're 1 meter away, okay? So you already know your distance, okay? What you're going to do, and they have several formulas here. Now, here's what the procedure says. It says adjust the ramp so that A, the uppermost portion of the ramp, is 10 centimeters above the tabletop. Do not adjust the ramp, okay? What you'll do is pick up your meter stick and find the place on the ramp that's 10 centimeters above the tabletop. You see? That's going to be your starting point, okay? And you can set that down. Find your starting point. You see what I'm talking about, okay? Yeah, 10 centimeters up, okay? This is 10 centimeters here. Yeah. Up, straight up. Okay. Make it 10 centimeters. That's going to be your starting point. Okay? So you don't adjust the meter, your inclined plane. You find the 10 centimeter mark. Okay? Now what you're going to do, I've already measured for you the horizontal part. What's that? 1 meter, right? The horizontal part is 1 meter. Okay? Now, what you're going to do, and I would suggest the person with the stopwatch be the one who releases the ball. Okay? You got your stopwatch? Okay? Now, what you're going to do, okay, is that exactly? Okay. All right. But you're going to have to hold it there. You can be lazy and let it hold it for you now. But what you're going to have to release the ball from there. Now, move this out of the way. Okay? You're going to release the ball from there. And what you're going to time now is not the time it takes it to roll down the ramp. No. Okay, are you listening? What you're doing is measuring the time it takes to roll from when it hits the table until it goes off the table. In other words, the time it takes to measure that, to go that 10 meters. Okay? Remember on the stopwatches? Let me handle that for a second. Okay? The 1 o'clock position is start, stop. That was 1.31 seconds. That's what you read on there. Reset is the 10 o'clock position. It sets it back to 0. So you start, stop here. Don't press the middle button. That changes the mode, and then I have to figure out some way to get it back. Okay? So you do your start, stop, and I get everything out of the way so it doesn't hit anything when it rolls here. Okay? No, you start at 10 centimeters. Yeah, but you start a time when you hear it hit the table, and then stop it when it rolls off the table.
So you
Okay.
started when it hit the table.
Okay, yeah. Try it once. Let go. Let go. Yeah, let go. Start. Stop. You see how to do it? Okay, you don't have to do that. Okay.
I did it when I
Any
was.
questions? Okay, we're going to get to that in here. Okay? Right now, you're interested in 10 centimeters up there. You got it? So get these things out of the way so you say, no, don't get in the way of the ball. And ultimately, we want this move too, but it's okay. Okay? Now, what you're going to do is release the ball from your point A, time how long it takes to move across the horizontal distance. Okay? And on your table, you see on page 70, it says projectile motion from a ramp 10 centimeters above the tabletop. That's what you do. You record 3 times. Now, if you get one of those times that's a wacko, way off, too long or too short, then do it again until these 3 are fairly close to each other. And then you calculate the velocity. How do you do that? How do you calculate velocity? Are y'all listening? How do you calculate velocity? You measure the time 3 times at 10 centimeters. How do you calculate velocity? Okay, yeah. V is equal to distance divided by time. So your distance is your 1 meter, and divided by the time, that's going to give you your velocities. Okay?
Start the stopwatch when it hits the table.
Okay, you start it when it hits the table and stop it when it rolls off the table. Okay. All right? So take your 3 measurements, record your 3 times, calculate your 3 velocities, and when you get to a place you have a question, stop and ask. Don't assume. Okay? And everybody help out with this, okay? All right. So you can start. Are y'all recording them? Okay. Page 70 is where you do that recording.
You said do it 3 times, right?
Yeah.
The same thing 3 times.
Okay. And you record those 3 times here. Time. Now, if any of them come out wacko, then go back to record that again. And nothing's in the way. Okay, I'm going to pause.
Yes, we got it.
Are you calculating your 3 velocities?
So how we're gonna do?
Okay, those are the seconds, right? Yeah.
So we're gonna what we got next is what we're gonna plot over here.
Yeah.
Right? So we're gonna do.
What's your distance from the end to here? And you measure.
We measured our 10.
Huh?
It was,
Okay, I know.
okay.
Well, what's the distance from the end there to here, where you measure the time? 1 meter. So 1 divided by this, 1 divided by that one, that's going to be your velocity. Okay. How y'all do it? Have you got your 3 velocities for 10? Okay. You got your 3 times for 10? Okay, good. Okay. What's your distance
I'm
from
gonna
there?
round up to
1 meter. And your velocity is distance divided by time. So that. Oh, by the way,
what are we rounding
notice your velocity is in centimeters per second, not meters per second. So you use how many centimeters in a meter? 100. So it'll be 100 divided by your time. And these are seconds. These are not meters per second. These are seconds, right?
So instead of 1, he's saying 100.
And then you divide 100 by that. You got 100 centimeters per second. That's right. And then you have to do a calculation. You have to, you need a calculator.
Point
You do, okay, because I brought a couple up here.
centimeter seconds. Does 0.884 centimeter second sound?
Say this again.
0.884.
Okay, remember you're measuring in centimeters per second, not meters per second.
Excuse me. So we said
What's that?
But, so he wants to round it. He wants to
That'd
round
be
it to
89.3 would be fine.
3, okay.
so I said 1 divided by.
No, it's not 1 meter. You're doing centimeters per second.
Okay.
So you do 100 centimeters divided by that. Divided by
1.13. And I get 88.4.
5.5.
Yeah.
I got a question.
Okay.
So the velocity I did, we do 100 centimeters per
Right.
second.
Divided by that.
By 1 point. So the seconds are going to cancel out, right?
No, this is centimeters.
That's centimeters.
This is centimeters. The length is centimeters, the numerator. The denominator is seconds, it's centimeters per second. That's what
So basically your unit's going to be 89.3 centimeters
per second. Exactly.
To get the average, we add them.
Okay, yeah, to get the average velocity, then you add the three together, divide by 3.
So you already did it.
It's not like we did last time. The last time we threw out high and low, took the middle. This time we're actually doing that. Did your 3 times come out pretty close to each other? Our average was 29. Our average was 29. Okay, yeah, but you just do the seconds, do the centimeters per second, add these 3 together, divide by 3, that's your average. Average velocity. Yeah. You're doing average V average, which is the centimeters per second. So you add these 3 together, and divide by 3.
Also, you add all 3 up.
Yeah.
That's, 1.13 plus 92.6.
Okay, yeah. Okay, wait. Okay, we're gonna get there next. Okay. Some of them are already up to the point. Let me see what you. Okay. Okay, wait a minute. How did you get that? This is the drop that you had is here. So I'll do it like this. Okay, the delta Y people, if you've already got your average, measure to the top of the table here, nearest 10th of a centimeter. The nearest 10th of a centimeter.
Am I supposed to do 3.03 divided by 3 or 3? Okay. Add them all up. I got 3.03. Okay. Add all these up.
No. You're adding your velocity, so calculate this one. Okay? And then add these 3 together, divide by 3. Yeah.
That's your vertical
Yeah.
distance.
Okay, vertical distance, that's what I'm getting to next. The vertical distance is how far the ball drops off the table. Okay? So what you do there is, take your meter stick, hold it here, and get the nearest 10th of a centimeter that it is from the floor. Did you get that?
I got 99%.
Y'all agree?
No.
Okay. Not off by much, but good.
80. Okay, good. I do the total first, then I divide by 3.
Right. And what was your first one?
88 seconds.
Oh, is that 88? 88. It's 100 divided by 1.13. See what that is?
What you say?
Oh,
He wants to measure from the top.
It's 88.
okay. Top of the table, yeah, near a 10th of a centimeter. Okay. Did y'all get your vertical distance? Oh, you bet.
Equals 299.619.
So we came up with 92 centimeters.
Okay, whatever you measure.
Okay, you got that?
Y'all got your vertical height? Okay, I'll do it from here in case there's any variation, so those are fell off.
So are we gonna do this here? We measure this here?
Okay, you already measured that. Y'all did good.
What you got it back?
So
It was first set up here.
oh no, we didn't. Yeah.
You gonna do centimeters? Okay.
How far is that? 1 meter, which is 100 centimeters. That's 92.
Oh, okay. So I thought we were using the calculator. Yeah, that's right.
Okay, all right. No, this is different. Delta.
Oh, okay.
Okay.
Yes, sir.
We're gonna say 91 and a half.
Okay, whatever you want to say. Hey!
She all scarred up. She's scarred up. She's all
Okay.
scarred up.
Y'all have to help her fill her in here.
Did you tone it? Lindsay, did you tone it out? We're sorry.
Okay, Lacey.
Hey. Now we got the other one. Sorry, Lacey.
Okay. Now, I take it that all of you are at the place to calculate the second delta H. This is a different delta X from before. Okay? What you're measuring now at the
Hold on, Dr. Fowler.
Yeah.
99 and a half we measured. Is that a delta Y?
what do you say?
Is that a delta Y?
Okay, that's delta Y. That would be measured in centimeters. Okay. All right. Now listen up. This pen isn't very good, so you may have to watch carefully. It says measure and record the delta Y. You all did that, right?
Yes.
Okay. Now, it says solve this equation, and here's the equation. Delta Y is equal to 1/2 G times delta X squared divided by
Oh, I love
V
it.
sub X
Yes.
squared.
Yes.
Okay. It says solve this for delta X.
Okay.
Okay?
Okay.
Now, y'all walk me through how to do that. What you want to do is solve for delta X, so what's the first thing you're going to do?
We're gonna chug and plug.
Well, no, move the things. Yeah, chug before we play.
Okay, we're gonna move a half over.
Multiply both sides by 2.
Right.
Okay, so that's going to wipe out the 1/2. Everybody see that? Okay, let me make sure I've got my computer on. Yeah, okay. We're going to multiply by 2. We also need to multiply by V sub X squared. So multiply by V, this isn't writing very well, V sub X squared. Multiply this by V sub X squared. So that wipes out your V sub X squared in the denominator. Okay? Now all that leaves you with is a G here, so we're going to divide both sides by G. Okay? And then, so here's what we got. If you get rid of the G's here, I'm going to reverse sides here. Delta X squared is equal to 2 delta Y V sub X squared divided by G. Everybody see that? Okay? We want the delta X, so how do we get from delta X squared to delta X? Take a square root. Take a square root, and that will give you delta X is equal to the square root of 2 delta Y V sub X squared divided by G. Now what's G, by the way?
The gravity?
Acceleration due to gravity.
Right.
What would that be? Y'all know the number? We've used it over and over and over and over again. 9.8 what units?
No, kill it.
9.8 what unit? Meters per second squared. But are we dealing with meters here? No, we're dealing with centimeters. So we need to get that 9.8. So the G is 9.8 meters per second squared. How many centimeters would that be? No, one more. 980 centimeters per second squared. So that's the number we use there. 2 is 2. Delta Y is what you measured. V sub x is what you averaged, right? Okay, and then the G is this 980 centimeters per second squared. You multiply and divide those first, take a square root, that gives you delta x. Okay? Anyone need a calculator? Huh?
Yeah, we
Okay.
lost over here.
All right. Can you see that? Yeah, I know, I'm left-handed. Okay.
I got that far with you.
Okay. Your delta x squared is, yeah, you got that, and then all you do is take the square root of both sides, and you got it. Now, this is little g, not capital G. That's the 9.8. The capital G was that number 10 to the minus 11. We're not using that. This is little g.
Which is 9.8.
You got it.
It's 9.8 centimeters
And
squared.
that G is 980 centimeters per second squared. I take the square root of both sides. This will just give you delta x, then this will give you your x.
So we're just dividing.
Okay, you're doing 2 times delta y times v sub x squared. That v sub x is what you just calculated,
Okay, so we
and you divide it.
So we're taking 92 centimeters.
2 times whatever that was, times your
2
This.
times 92. 2 times 92 centimeters,
Right.
right?
times this thing squared.
Times 91.8 squared.
Yeah, okay, divided by 980.
So where do we get 980 from?
That's
That's
your
the,
9, G is 9.8 meters per second squared, but everything you've got here is in centimeters. So that'll be 980 centimeters per second
So
squared.
how did we get G being
Because
980?
that's the
What's that?
formula. That's the formula, right? For G. 98.
Okay, G is the acceleration due to gravity, 9.8 meters per second squared, right?
That's the
We use it
formula.
over and over and over. It's a constant on the surface of the earth. Acceleration due to gravity, 9.8 meters per second squared. But we need it in centimeters, so we change that to 980 centimeters per second.
Instead of 9.8.
Yes, exactly. Because you multiply by 100 to get centimeters. So
980.
that's your G down here. So it's 2 times delta y, which you measured, v sub x squared, you calculated v sub x, square that, divide by 980. That whole entity, take a square root, that gives you your delta x.
So basically everything's gonna be wrote the same. You're just gonna put 980 at the bottom of it instead of the G.
Right, instead of G, that'll be 980. 2 times delta y, which you measured, v sub x, which you calculated, squared, divided by 980, that's your G, and take the square root of that whole thing, that gives you your delta x.
I'm not squaring it equal. No,
What's that?
is it 0.01?
Yeah, you can do your fractions down here and just write the number up there.
Did I do that right? 92, you said 2. That's the delta y times 2, right? And then that 98.8 squared. Squared. And then divided by
980.
980.
980. Once I divide by 980, I need to square that.
No, okay, no. Let me see what you put in so far.
I said 2
What did you do that right there? I thought we multiplied, once we got this answer here, we multiplied that. See, I
Square.
don't have a
Square
calculator to
that.
do the square.
Divided by
divided by 980
equal.
Let's add slice it.
not square.
Let's
Square root.
slice it back.
41 times 42. 43.
We got everything.
43.2.
Okay.
So,
right with the correct hand, good. 2 times delta y is 92. Well, you can do all this and then take a square root at the end. That's the easy way to do it, yeah. But yeah, it is all in the square root. The delta y is 92 times, if you want to, it'll get a little messy, but you can do it. Okay. Times 91.8, that's your delta, that's your v sub x. Then you're going to square that number. Okay, then divide that by 980. Okay, and then take the square root of that whole thing. Yeah. If you got a calculator, the calculator will keep up with it.
So we square root twice. We square root twice.
You take this. Where's your formula? See, this is a square here.
That's the square.
And this is the square root. Okay, so square one, square root 1.
2 times 91.5 times 98
Square divided by 980 equal. Now take the square root. Everybody see that? Does everybody have your delta x?
Not yet.
Okay. How are y'all doing?
Seconds, I believe. That's what we did again. So that'll be in seconds, won't it, Dr. Fowler? Patrick, would that be in seconds? Centimeters. Centimeters. In centimeters. Sir. See, with these kind of calculators, I didn't know what kind of calculator. You probably ought to start with the square root. That'll make it a lot easier. And you don't have to mess with the answer. Okay. Okay.
Okay, he's already moving to his next step, okay? Yeah, you were doing right. Okay, you estimated that to be, what did your answer come up with? Okay, and you measured that approximately there, is that right? Okay, however you did it, okay? And then line it up with here, I made it a little bit, okay? Now roll it from that 10 centimeter and see if you get it up. Oh, look at that!
Who was that? Who was that?
Okay.
Who was that? Who was it? I'm talking about like LeBron James.
Probably the
This ain't gonna, I don't think gonna be good with the same lenses.
So I gotta take that off.
Yeah.
That's the only thing gonna be good.
3.9.
That's the only. Hey,
Or move the test
That's
to
it.
1, that's 39.8.
So
that's it.
Hey, you saw the playoff.
No sir, no sir. I've been tied up in
That's where,
this crap.
like you said, it
Oh yeah, well,
centimeters per second squared, so centimeters per second divided by centimeters per second squared. So you know, centimeters cubed up here, centimeter down here, centimeters squared per second squared, and then you take the centimeters. No, I mean centimeters. Okay. So did y'all do your calculation?
I'm jealous. Wait a minute.
This way. Look at me.
You calculated what the delta X would be. So you come down here and then you have to estimate where that is on the floor. Line up with this, and push the cup.
We got different numbers.
You're coming
I
off
measure
this.
the distance of the cup.
Flip it over. You got inches on it. Flip it around.
I think it's the third step on page 68.
Calculate your delta X.
Place a cup. No, it's three. Place a cup. Place a cup on the floor and calculate the distance.
Be sure it's lined up with your right.
Oh my God, it's make it this good.
Yeah, that's the key. That's whether you pass or fail now. No, I'm just kidding.
Alright, let's see. Sorry guys.
Read to me. It said place the cup on
Okay,
the
move
floor.
the stuff out of the way.
No, not myself.
What are you doing?
This is 20 here. This is
Okay, move your stuff. Alright, let's see how you do.
Hello.
Yeah. Try down again.
Oh, so
close.
no! This game is pretty.
The other way.
A little off.
Did it hit this way?
Yeah, it did. That was
So
fun.
39.
That was just for fun. You won't have to do that anymore.
Okay.
Now you do your other two. Oh, so close.
You ain't gonna hit it.
Okay.
I mean, it would, but the cup's gonna be too far to the
So we're
right.
gonna do the cup out now?
Okay.
So,
Okay, get the stuff up.
so you need a ruler there?
No, it doesn't have.
It's never gonna hit that cup.
Where is it?
Far to the right.
Well, move the cup. Line it up. Oh, okay, yeah, it would have hit it.
Yeah, it's just that it's, I think it's.
All you have to do is.
Stop it when you go.
I wanted to go in. It's still a little crooked. Still a little crooked.
Okay. Let it fall. Oh, look at that! Bring
I
it.
missed that with the eye.
Okay.
I missed that
Yeah,
with
then
the
you
eye.
got to 27 minutes. You don't have to do something.
So what, so, okay.
Take too long. We want to get out of
So
that.
using this, okay.
1.8.
31, 3, for the round height.
Sure.
Okay, so now we're.
All right, I'm going to turn off the we're on procedure. Results on page 68. Make a graph with the velocity on the horizontal axis and distance on the vertical axis. Use the average Vx for velocity and the average delta x for the distance. Okay, no. Yeah, and the distance, on the y-axis, the vertical axis. Okay. Now, what you do there, if you've got your numbers already, call out to me. Okay, again, you want velocity on the horizontal axis, distance at your delta x on the vertical axis. Okay, I want you to call out to me your 3 Vx's for 10, 20, and 30. Approximately what numbers are they?
On 10, you got 91.8.
Okay, wait, just a second. Let me write this down. This doesn't have to be exact for everybody. What is it?
91.8.
91.8.
On the 20, you got 124.
124.
On the 30, we got 152.1.
152. Now that's your V sub x, right?
Yes.
Okay, give me the same for your delta x.
Delta X on the 10, we got, they're all 92.
No, delta x, not
X,
delta y.
oh,
Sorry. Oh, 39.8. 53.7.
53?
Yes, sir. 65.9.
Okay. Now, this was your V sub x, and this was your delta x. Okay? Now, here we go. What you want is the velocity on the horizontal. This is horizontal. And this is vertical. Delta x on the vertical. Okay. Now you see you have a bigger range here than you do there. So what I would do, the horizontal, I would draw my axis so it's the V sub x. Gotta find it. Okay, here we go. Draw it like this. Your V sub x's are going across here, and your delta x's like this. Now you're going up to, let's just call that 160. You have 1, 2, 3, 4, 5, 6, 7, 8. So if you do 0, 20, 40, 60, 80, 100, 120, 140, 160, that's going to cover your V axis. Okay, going upward, you have 1, 2, 3, 4, 5, 6, 7. There you have it. 10, 20, 30, 40, 50, 60, 70. And that will do quite nicely like that. Now, if y'all have slightly different numbers, they're probably going to be fairly close. Is that right? Yeah. Did you see or hear what I was saying?
Yes.
Okay. That's the reason
We can skip. We'll make two squares right now.
That, okay, what you have is this average. Hopefully this average here.
250.
Let me take a look what you have here. So this is your 10, right? Yeah, those are your 30. Added there, divided by 3. So this is your calculator. So it's not far off from what they got. Okay? This one, you should average these 3, and that's what it is. Yeah. These, not the
Let's go 10. Let's go 10.
Now, that changes everything, but eventually you plug this in and the other way. Over here, those
We gotta go to 200.
because see, you found this 0.75 here. This would be faster.
That's gonna be this way. this, this.
The last one, you talking about the 1.81? Yeah, I should have said we caught that. It was probably 1.8. We were, I don't know, I should have caught
This
that.
goes.
That should be where.
From 30 to here. Do those three.
Here it is. Oh, it's 1.8.
So this is his four. Okay, so call the distance on.
That's 65.
This is
This is the
BS.
vertical. So we gonna go
Yeah, and we're calculating the velocities.
I should have caught that.
I'm guessing all three of these are.
Yeah. The things we have to write it down.
I'm going to shut down recording.